Hello, my name is Joshua Ferrer, and I am taking Physics 2211 at Georgia Tech, and this is my lab video. This lab will be split into two parts. The first is about finding the mass of a black hole using a computational model, and the second is about finding a trajectory to escape the black hole. Like I said before, the mass of a black hole will be the first part of a lab, and the trajectory to escape a black hole will be the second part of a lab. This lab will discuss two key concepts, the first being Newton's second law, which states that an object's acceleration is dependent on the net force being applied to an object and the mass of the object. Velocity, which is also related to this, is a function of speed, which uses in meters per second. And gravitational force is the force that a large object, sometimes a planet, applies to a smaller object, in this scenario, a black hole to a ship or a planet. The purpose of this lab was to use a computational model to find the mass of a black hole and the trajectory needed to escape it. On the left, there are four equations, which will be used in the first part of the lab. These equations relate to the parallel and perpendicular component of a lab, and these combine to equal the net force total, as shown here. On the right, there are three equations which relate to the second part of a lab that detail the gravitational force. In particular, this equation and this equation will be used later. And the system of both part of the labs of the model is a ship, and the surrounding is the black hole. Now for the first part of our lab, finding the mass of a black hole. Before I go over the code in details, the computational model itself produced this data once it was running, using the equations from the previous slide to find Fnet parallel and Fnet perpendicular and Fnet total to produce the mass of the resulting black hole as you see. Moving on to my computational model, I use Python to create the code in Glowscript. The initial conditions for the method are shown. In particular, I want to call to attention the gravitational constant and the mass of the star as you see here and here. Now for the code itself, I used the equation stated before to calculate momentum in each component, parallel and perpendicular. As you can see on these lines, I calculated the initial and final velocity of a star and delta V and delta P, use that to calculate dp dt, and use that to calculate the net force using Newton's second law. From there, I use that to calculate Fnet parallel, Fnet perpendicular, and use the total of that to calculate the mass of the black hole overall. Now I'm going to show you the finished product, which is the model itself and a video of the black hole moving itself. One sec. And as you see here, there are three lines. The pink line, as you see here, is parallel to the circle, and the orange and cyan are perpendicular as they point to the center. Now for the second part of the lab, finding the escape trajectory needed to approach and leave the black hole. Now before I go over the code in details, the computational model itself produced this data once it was running. As you see here, the planet's orbital speed, planet's orbital period, and the distance from the ship from the event horizon of the black hole. Now for the initial conditions. In this scenario, we use the mass of the black hole from the previous part, as you see here, and we needed this to calculate the gravitational constant formula. Next, we have math to calculate the planet's velocity and speed, as you see here. And finally, the ship's speed, x and y, I found through trial and error to find a scenario where the trajectory could escape the black hole. Now, the code itself is mainly just a repetition of the gravitational constant formula. As you see here, for example, this is actually just g mm divided by r squared, as you can see here quite literally. And this is really just repeated over and over to represent the gravitational force on, for example, the black hole to the planet, the ship to the planet, the black hole to the ship, or the planet to the ship. And after all of that, we were able to calculate the final net force right here. Now, this is the actual video itself of the ship approaching the black hole. The purple line is the trajectory, and the blue line is the orbit of the black hole. Now, this is kind of weird, the actual shape of it, and this is probably due to some error in my code. A small error that caused it to look this weird, because it's not supposed to be a straight line like that, but it does escape the black hole. But what does it mean? Discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum. Well, there is no difference, as they are both equal to each other. The main difference is that the rate of change of momentum can be calculated before part 1 of the lab is complete, meaning we can do it before knowing the mass of a black hole. Now, what if? What initial velocity would a spaceship need in order to enter into some kind of orbit around the black hole? Well, knowing that a planet's orbital speed is 8.6 e to the 6 meters per second, it can be assumed that to enter an orbit around a black hole, the ship must be equal or greater than its speed, similar to how a rocket must accelerate to a great amount of speed to orbit around Earth. Thank you.